Okay, we have another beam problem with a distributed and variable intensity load. This particular problem is set up in a very realistic scenario, and therefore a simple kind of thing actually begins to be kind of complex. All right, what we've really got is a roof that covers, a roof beam that is, that there's the interior part of the building, and then there's an overhang on the exterior. And usually on buildings you'll find out that there's a parapet, and that parapet, as it is extending up, is going to be a place where snow can collect and get deeper with the drift. Out here it might go down to zero at the edge of the roof overhang, and then at some point the drift ends and you just have this base snow layer. Right? So we got a lot of information provided here that's in text form, so let's get that written down to figure out what's really going on here. And then we're going to step our way through the problem. Right? The roof's beam spans between supports. All right, so the span is between supports, and that is 20 feet. Right? The overhang is 5 feet. Not a big overhang, but it's a little one. It's there. The peak height of the snowdrift is 3 feet, and the snow has an approximate density, unit weight, not mass density, of, that'd be gamma equals 8 pounds per cubic foot. Right, so that's the, wow, snow density is incredibly variable. This is just kind of a crude average, it turns out. Right, and let's see, what else are we given? Assume that the beam supports about 5 foot of the structure in and out of the plane of the paper. That's a typical little roof beam. Right, so you have to imagine that we have a little beam sitting here, and there's equivalently a slab that is 5 feet wide that this beam is supporting. Right, that's the cross section of the beam. Let's just fill it all in. Right, so that's what that's all about. In and out of the plane of the paper. Well, is it 5 feet total, or is it 5 feet either side? It's not really clear the way it's stated, so we're just going to assume that means 5 feet total. The drift between supports extends 9 feet. Right, so this drift down to the toe of it, all the way out here, is 9 feet. Alright, snow base on the middle span is about 16 inches. Right, so that's this part here. So that height is 4/3 feet. Wow. Find the magnitude of the distributed load at the critical points. Right, so what I'm going to do is redraw this setup. And actually what I'm going to do is essentially a free body diagram. There's the beam, and the intensity of the load is going to follow the depth of the snow. So it's going to look something like this. Right, and we've got 1 and 2 different intensities. This is uniform all the way out, so there's not anything more to do there. Now we have a reaction. Let's call that A. Let's call that B. So that would be AY. We've got a BY, and we have a BX that will of course equal to 0 by sum of forces in the X. Alright, so now how are we going to find this W1, W2? Let's do the base sort of uniform little load out here, W1. Alright, now check this out. We've got 4/3 deep, 4/3 foot deep. Right? We've got, so that means snow 4/3 foot high, 5 foot wide, at a unit weight of 8 pounds per cubic foot, which means, look at the units, feet here, divide into this, we're going to get pounds per foot along the length of the beam. Right, so that's 4 times 5 times 8, 160, not nicely divisible by 3, so I'm just going to leave that as 160 divided by 3. Pounds per lineal foot is what that symbol means. Okay, that's the same thing as just writing pounds/feet, but that's not a nice typesetting thing to do, so we just write it as PLF. If it was 1,000 pounds per foot, that would be kip per foot, KLF. Right, W2 then is our other peak that's at 3 foot deep times 5 foot tributary width times 8 pounds per cubic foot for the unit weight. And so now we get a little bit nicer number. 3 times 5 times 8, 15 times 8, same thing, 120 pounds per foot. Now that seems like less. Oh no, that's 160 divided by 3, a little bit, about 53 compared to 120 there in the intensity. Right, so that's 160 divided by 3 PLF, and that's equal to 120 pounds per foot. Right, now let's estimate the reactions due to now these loads, being just the snow load, not the self-weight of the beam, just the snow load. Right, now we have a little bit of an overhang, so it's not as though AY is going to get half of the total load here. It's going to get a little bit more with this overhang. I don't know, let's estimate that AY gets, I'm going to say about, I don't like 55%, I think that's too low, I think 60% is too high, so I'm just going to guess 0.58 of the total, right? And what's the total? Well, that would be 0.58. Now I could just make some sort of crude approximation for this whole thing, but you know, I can do this pretty easily. This is a triangle, 1/2 of 5 feet times this intensity here at 120 pounds per foot, plus, then we get a little triangle here that's 120 minus this 53, so that's 73.33, and I think, maybe-ish, maybe not. Let's just call it 73 pounds per foot. That's the height of this triangle, and it's 9 foot long. Plus, then we got just a regular rectangle, that's 160 over 3 times 20 feet. So let's find out what I'm approximating is the middle part. I got a little sloppy there with that 73 because I just wanted to go fast. And that says about 1,400 pounds times 0.58. That says approximately 814 pounds. I'm suggesting is AY. BY then would have to be only 42% of the total. So that would be the difference, or about 586 pounds. All crude approximation. Let's go find out what the real answers are. Right? So now we're going to do this for real. Determine roller reaction net, do the snow load alone. Right? Well, some moments about point B, that's the far right. Let's take clockwise positive, so we'll have 20 feet times AY. That's the easy part. Then, minus, this load's going down, right? It's going to be at 5 divided by 3 away from the support, so its moment arm is 20 feet plus 5 over 3 feet, times its magnitude, which is going to be 1/2 of the base of 5 feet times the height of that triangle, 120 pounds per foot. So that'll be pounds, and then times feet, so we got that part all right. And then now we have to do this one for real, that little triangle. Its moment arm is, alright, so it's 3 feet, because that was 9, that's 1/3, so 20 minus the 3, it's at 17 feet away from B. Alright, we're taking summation of moments about B. And we got to get the magnitude, 1/2 times that base of 9 feet. And then we got to get the height of that triangle. It's 120 minus the 160 over 3 pounds per foot. 120 minus 160 divided by 3 is 66.67. So I was wrong when I said 73 before. So that was an error, right? But it's an approximation. I was going fast. I wasn't trying to be exactly right. Alright, so that's that one. Then we got to do all of this rectangle. Well, that's uniform, so that's going to be 20 feet times 160 divided by 3 pounds per foot. And its moment arm, oh, I already got, oh, hey, the moment arm is 10 feet. So that was just the base of the rectangle. Alright, so I didn't do the moment arm in the same order as I did it for these others. Set that equal to 0. Well, let's work this out into some detail here. 20 feet times AY is going to be equal, this first number is 20 plus 5 divided by 3, 21.67 times 0.5 times 5 times 120. That's going to be 6,500 pound-feet, right? Pounds per foot times feet gives us pounds, pounds times feet, pound-feet. Right, so that's that one. And then we got 17 times 9 divided by 2 times the 60. I still think I wrote that wrong down. Let's get 120 minus 160 divided by 3, 66.7. Okay. Equals, I have no idea if I did that right, 17 times 9 divided by 2 times 66.6, and we get basically 5,100. For all that one. Of course, taking the other side. And then we get 20 times 10 times the 160 over 3, so same thing as 200 times 160 divided by 3, and that feels wrong, but let's do it again. 20 times 160 divided by 3 times 10. We get a big number there. Well, it goes all the way across. So the total of that is 22,266 and change pound-feet. And then we're going to divide that by 20, and AY is going to be equal to 1,113. I don't think that makes any sense. I had to have made a mistake. Yeah, I'm sure I did. So 20 plus 5 divided by 3 equals times 5 feet divided by 2 times 120 equals 6,500. Okay? Now this is a little one. 17 times 9 divided by 2 times 120 minus 160 divided by 3. That's 5,100. Guess I didn't make a mistake. 20 times 160 divided by 3 times 10. That's a big number. And we get 1,113 pounds. Well, what did I say? I said maybe it was about 814 pounds. Oh, well, that's not that far off. And this was more exact. I knew I made a mistake on the 73 here. And maybe I wasn't really doing sum of moments at all, was I? No, I sure wasn't. Right? And let's just check and find out the total load real quick. And so the total load of these little pieces up in here, 5 divided by 2 times 120 plus 9 divided by 2 times 66.67 plus 160 divided by 3 times 20 feet. And the total load is actually 1,667 pounds, so I underestimated that. Hey, look at that. Oh, wow. So AY is about 2/3 of the total load. That's kind of interesting, to me anyways. So I underestimated what the reaction might be over here. That more load is piled up, more load is piled up over that support A than I was anticipating. But hey, we still got it right. It's cool.